reflecting over a line that isn't one of the axes, or y equals x or negative x. Take, for example, the line y equals 4, shown here. I've added in the point 2,5 to show the transformation more clearly. We recall that to reflect over this line, it is a 3-step process, which first involves moving everything down 4 units such that the line lies on the x-axis. So everything will move down 4 units accordingly. Next, we need to reflect the point over the x-axis. So the reason we moved it down was to make it easier to do the reflection. So now we've got our point to -1. The last step is to then move everything back up 4 units. And you'll notice that the point ends up at 2, 3, which is indeed the reflection of the point, the original point, 2, 5, over the line y equals 4. So just to recap, recall that this process takes 3 steps. Move it down, reflect, and move back up. And that is the resulting transformation. Now we're going to take a look at a line that is not horizontal nor vertical, but goes through the origin. This is the line y equals 2x. So we're going to use the point 1, 0 to demonstrate what happens in this transformation. We need to relate this back to the 3-step process of reflecting over the line y equals 4. In this case, instead of moving up or down, we need to rotate such that the line lies on one of the axes. So first, I will rotate the line clockwise to lie on the x-axis. You'll notice that the point will move clockwise accordingly, but always staying the same distance away from the line. We then need to reflect now over this x-axis, which will keep the x-coordinate the same and make the y-coordinate the opposite sign. And then just like in the other process, we need to then rotate back, in this case clockwise, the same amount. And you'll notice that the point ends up at -0.6, 0.8, also known as -3/5, 4/5. And it looks perfectly reflected over this line y equals 2x. So just again, to recap, we need to take the original point, we need to rotate everything theta. In this case, theta is the inverse tangent of 2, because the slope of this line is 2, and we remember that the tangent of the angle is equal to slope. So tangent of theta equals 2, so theta equals inverse tan of 2. After we've rotated clockwise, we need to reflect over the x-axis. And last but not least, we rotate back, and that will give us our final image after reflecting over the line y equals 2x. Now we're going to actually come up with the matrix that performs these 3 transformations. To recap, the rotating clockwise by theta, which we'll call T1, the reflecting over the x-axis, which we'll call T2, and the rotating counterclockwise back by theta, which we'll call T3. Now we're going to do this in terms of theta to keep it more general, but just remember that the tangent of theta is equal to the slope of the line, because it is equal to the rise, the y, over the run, x, also known as slope. So in this case, tangent of theta is equal to 2, which would imply that theta is equal to the inverse tangent of 2. But instead of having to write inverse tangent of 2 every single time, I'm just going to keep everything in terms of theta. And if you wanted to do this with a different line, you could then apply this to a line with any slope, so long as it goes through the origin. So here, just to recap from our previous work, are the 3 transformation matrices in question. T1 is the matrix that rotates theta clockwise. You'll notice that the negative is in the first column, If you think about the image of the point 1, 0 after transformation, you can think about it moving down into quadrant 4. This second matrix here is the reflection over the x-axis. You'll notice the first column is just 1, 0, since that point would not be moved after reflecting, but the point 0, 1 will now have an image of 0, -1. And last, we're very familiar with the rotate theta counterclockwise matrix, as we've seen before. We also remember that when we compose transformation matrices, we have to do them from left to right. And so we write them T3, T2, T1. And that's because when we include some kind of point to apply this to, it's happening closest to the T1 matrix, and that's going to be the transformation matrix that happens first. We also know that since matrix multiplication is associative, what I did here is I multiplied the first two matrices together and got cosine, sine, sine, negative cosine. And then I multiplied those two matrices together to get my final transformation matrix, which we see down here. So you can take a moment and pause and think about where these sort of equations came from. Now, you might want to do what I did the first time I looked at this problem and use trig identities to simplify, but we're actually going to keep them just like this for the time being. So now we've hit our last step, which is to simplify this in the special case where the line is equal to y equals 2x. And we remember that theta, the tangent of theta, is equal to 2 because that is the slope. Well, if tangent is 2, what are sine and cosine? So we can kind of turn this line into a right triangle. And since we know the rise 2 versus the run 1, we can use the Pythagorean theorem to solve for the hypotenuse, which would be root 5. And since we have the hypotenuse, we know that sine of theta is opposite over hypotenuse, 2 over root 5. We know that cosine would be 1 over root 5. And from there, we can actually go and simplify each one of these trigonometric expressions. Instead of having thetas, we can plug in what they're equivalent to. So this would be 1/5 minus 4/5. It would be 2 times the product of sine and cosine, which would be 2 over 5. So 2 times 2 over 5. Because those root 5s, root 5 times root 5 is 5. Same thing down here, 2 times 2 over 5. The last term would be 4 over 5 minus 1 over 5. And so finally we can do a little bit of algebra just to simplify. And we'll get our final transformation matrix after all that work. The product of T3, T2, T1 is simply -3/5, 4/5, 4/5, and 3/5. And so again, if you had a different line, or for example, a line with an unknown slope, you could do this in terms of a variable, like m, or you could do this in terms of a different slope number, like 3 or something like that. You would just have to solve individually for sine and cosine. So that is the process of reflecting over any line through the origin.